All right, anything you want to look at before we get going again?
Yeah.
Yeah.
So like we did understand how we're supposed to do like the ones where it gives you like your C with two equations with X and Y in it, but there was some that it was like, was like F of X, Y is just a vector. It's like 8I, 8J or something, and then it gave you 2 points, and it wanted the integral, and I did not know how to do that with.
Is that number 7?
Yeah, I think so.
I had to have the tutor help me out with that. I had no clue.
I don't have the book, but
Oh,
no. Do you have your
yeah,
book?
I have the book right here.
okay. Take a look. I have the book in my office, but it's ripped back. I'll start to write something up there while you look that up then.
F of xy equals 8I plus 8j.
Okay. On the vector, 8I plus 8J,
Uh-huh.
okay.
I'm sorry. It's 15.2. Number 7, number 9.
Okay,
Put it back in the class.
okay. Thank you. And then find F dot dr along this line segment. There's F as the constant vector, and then find line integral F dot dr along segment, line segment, number 7, 8.2, from -4, 4 to -4, 5. So this one, we're going to talk about this some more tonight, about other methods, but by the first method, we can say that the integral along C can be gotten by writing parametric equations for this curve C, which we'll draw on the plane just to have a better feeling for it. -4, 5, oh boy, -4, 4. So it's just a unit line segment going that direction. C. We can write parametric equations for that very easily, right? See, what you do is you say x equals x0 plus at, y equals y0 plus bt. For the vector through the point, we can choose -4, 4 for x0, y0. And then we need a vector from here to here, r0, or v, we usually call it in the book, is the differences in these components. The difference in the x coordinates, -4, minus a -4, 5 minus 4. So the direction vector is just 0, 1. So we write parametric equations immediately as x equals -4 plus 0t. These are A and B. To write parametric equations for a line, you take a point of the line and a vector parallel to the line, 0, 1 in this case. And you just write x0 plus at, y0 plus bt. Right? So this is -4 plus 0t for x, y equals equals 4 plus 1t. There's parametric equations for the line. Now you don't actually have to do so much figuring for this line. It's really easy, right? Oh, without subtracting it. So you can just take -4 plus 0, 4 plus 1t. So you don't have to do this much figuring, you can see it, but, so we drop this off and it's just x equals -4, y equals 4 plus t. Parametric equations. Now we'll say the integral along the curve f dot dr, this is actually a good example leading into that, is the integral, you can change it to the integral from a to b of f dot and replace dr with dr dt dt. This is how we evaluate a general line integral. Is we'll just change the dr to dr dt dt and run over the endpoint t. And now
Can you zoom in the camera?
zoom it in, okay. Let's see. There we go. Hopefully that's better. And now f is this vector 8, 8. We can also write it in this form, 8, 8. And so this is 8, 8, just to use the same notation on both, dot. What is dr dt? R is the vector that has these components, right? So if this is the parametric equations, R of t is x of t I plus y of tj is minus 4 I plus 4 plus t j. That's R. Basically write it in the other form. 4 plus t are its components. So minus, it's 8, 8 dot this vector minus 4 plus t dt. That's all you have to do to evaluate that line integral. And so 8 times minus 4 is minus 32. Plus 8 times 4 is plus 32. Plus 8 times t. All integrated with respect to t. And t went from 0 to 1 on here. You can either, whenever you do a segment between 2 points this way, t runs from 0 to 1, because if you put in t equals 0, you get the initial point x0, y0. If you put in t equals 1, you get x0 plus a, y0 plus b, which then goes to the second point.
Wouldn't the second, like you have the vector AA dot -4 plus t? I thought that was dr dt, so wouldn't it be the derivative of that?
Oh, yeah, I'm sorry, I miswrote that, didn't I? Yeah, it's the RDT. Oops. Yeah, thank you. It's derivative of this one. I started doing that, I forgot. RT is that, and R prime then, thank you, is 0, 1, yeah. The derivative of R.
So then that would change the numbers on the bottom.
Yeah. And so this is now, 0 to 1. 0 plus 8 is 8. dt. This becomes 8t evaluated at 1 and 0 is 8.
So A and B.
Because when you put in t equals 0, the parametric equations, it's there, these parametric equations, 0 less than or equal to t less than or equal to 1 sweep out the line segment. If I put in t equals 0, I get the point minus 4, 4. If I put in t equals 1, I get the point minus 4, 5, the other end. Yeah. Whenever you do this kind of a formulation where AB is the vector from first point to the second one, then T just goes from 0 to 1. Because what you do is you get, this is the vector x0, y0. And if you subtracted the coordinates between these two, then this is the vector AB. If you take x0, y0 plus AB times 1, then you go to this point. And that gives you the second point here for equals 1. So this one, the first point is always R of 0. Second point is always R of 1. If you get AB by subtracting the coordinates of the point. All right, so that's a good lead in because our next thing is to remind ourselves of what we were doing last time for line integrals. Last time we had vector line integrals. And I think this section is rather confusing. there are scalar line integrals that we did first, the area of the curtain. And then there's a vector line integral defined in terms of the scalar line integral. But the vector line integral comes in three different forms. You can integrate it along C, f dot dr, given a vector field f. You can take an integral of f dot t ds, given a vector field f and t the unit tangent along C. Or you can take the line integral along C, f of x, y, dx plus g of x, y, y. And these all mean exactly the same thing, just in different notations. So these are all the same thing. This one, in fact, if you just put f of x, y in this thing here, and you can do this in more dimensions, h of x, y, dz, if you have 3 dimensions. If you put f of x times I plus little g of x, y times j, this whole thing here is just a fancy expression for f dot dr. dr being dx dy. So this is another way of writing this. What is this? This was defined to be this. So these are actually the same thing. And all three of these are the same integral, just in 3 different notations. This is writing the vector field with the components f and g. You can write it this way if you want. If you just want to write the vector field itself without specifying the components, you can write it this way. If you want to write the definition of it, it means this way. How do you evaluate these? What you do is you, for this one, you simply rewrite it. So here's the notation, 3 different notations. These are the same, they're all a vector line integral. And you just take f dot and you replace dr with dr dt dt and integrate from a to b. And along any smooth curve with f continuous, that works. So this is how you evaluate it. If you see this, do this to evaluate it, right? Treating it like engineers, you're not doing the proofs, but just reminding you of the theory. You don't do it this way, you realize that this is actually f dot dr. Right? F dot dr is defined to be this. You could do it as a scalar line integral, but the easy way to evaluate it is to just go back to this formula. So you leave out this intermediate step. You also convert it to f dot dr dt dt. Either one of these, you just write f dot dr dt dt from a to b, just like we did in that example. And you can evaluate it. That means you have to write the curve in parametric form and find out the limits of the parameter a and b. How do you do this one? Again, this is just another way of writing f dot dr, so it's the same thing, but it's preferred probably to just replace dx with dx dt dt. This is the easier way, right? X is a function of t, y is a function of t along the curve. Replace dx with dx dt dt. And then evaluate g along the curve, x of t, y of t. Replace y with dy dt dt. And so you just rewrite this one like that. Dx is dx dt dt, dy is dy dt dt. dr is dr dt dt, and you can evaluate all those things. So that's the trick to getting through those. You just recognize that 3 different notations for the same thing, and just write dt dt, chaining along to figure out how to evaluate the integral. Then we said, well, this can be really difficult sometimes, depending on how the integral comes out, right? If it's a tricky integrand or if it's a snaky path, right? It might be really hard to evaluate the integral along the path. Isn't there some other way? And we had at the end an alternative that only applied if f was conservative. If f of x, y, a vector valued function, so it's a scalar function f of x, y times I, plus a scalar function x of y, g of x, y times j. If that vector value function is continuous, meaning little f and little g are both continuous functions of intervals along the path, well, we'll just say continuous. It means on an open region containing the path, I think is the way it goes. It is continuous, and C is piecewise smooth, meaning it's a finite number of smooth pieces put end to end, including the case that might just be one smooth piece. X0, Y0 to X1, Y1. And finally, F is conservative. This is the big one. What does it mean for a vector value, vector field to be conservative on an open region containing C? What does that mean, conservative?
One with the phi symbol.
Yeah, with the del symbol, if, yeah, with phi in it, yeah. If f, the gradient of some function phi. So in 2 dimensions, it's f of x, y equals gradient of scalar function phi of x, y, just an ordinary function. Say scalar function. Then it becomes trivial no matter how complicated the piecewise smooth path. It can have a million billion different pieces. And they can be twisty turning all you want as long as they're smooth. And what you get is that the line integral in any one of those notations, I'll put f dot dr, but it applies to all three, is equal to the potential, corresponds to potential energy in physics, minus the potential in physics. F and put f is minus the gradient of the potential with phi potential function for f. The line integral is just phi at the final point minus phi at the initial point. This only applies to conservative vector field, but as we said, they're also very important because some the 1 over r squared force field, gravity and electric fields, for instance, is conservative. And other ones, for instance, the mass on a spring problem in physics, where they corresponds to vibrations and beams and so forth. They use that model, is also a conservative. All right, so that's the big theorem, and now we want to do some examples of that. Maybe a calculus 3 lecture there for a second. Close this one. If f of xy is equal to x squared yi plus 5xy squared j. We can first ask, is this conservative? And apply the theorem if it's not conservative. How can we tell? There's actually a short way. For now, we'll do it the long way. What we do is call this little f, and this little g is in the theorem. What we need is that the gradient of some function phi is equal to the vector with little f little g, right? But the gradient of phi is df is d phi dx d phi dy, so this is equivalently d phi dx has to be equal f, which is x squared y, and d phi dy has to equal g, which is 5xy squared. Can I make those equal? Well, it's kind of hard to tell, but this is a partial integral, so I have a partial derivative. I can solve for phi by doing a partial integral. So by partial integration, meaning take an integral to keep the other variable constant, I say phi in the first equation must be equal to the partial integral of x squared y with respect to x, right? Partial derivative with respect to x, I take the partial integral with respect to x to undo it. This means I treat y as a constant, so I got x cubed over 3y plus an arbitrary constant, which I will call h. And now I realize, wait a minute, when I take a partial derivative to get back this integrand, I treat y as a constant, so h is actually an arbitrary function of y. The arbitrary constant in partial integration is an arbitrary function of all the variables that are held constant, in this case just y. So all functions that have this partial derivative are this form, x cubed over 3y plus h of y. Now I also do partial integration on the second one with respect to y. I get phi on the left and integrate this with respect to y. And let's see, 5xy squared integrate with respect to y, treating x as a constant, is 5x arbitrary function k, let's say, of x. X was treated constant in this interval. These are all functions who have partial derivative with respect to y equal to 5xy squared. And now, can I make those meet equal? Can't, right? To make this equal on any open region, I can't. I can make it equal to a point by choosing x and y correctly, but I can't make it in a region. So no, this is not conservative.
We take the partial integral with respect to x and then respect to y. Is that equal?
That's, boy, you read ahead. Okay, yeah, that's coming up. Yeah, yeah. Okay, yeah. I'm impressed you remember that. That's good. So there's that one. No, because I can't make these equal. And maybe I should just do it now. I was going to do another example with it is conservative, but let's go ahead and make this following notes and bring up the theorem. There is an easier test on a simply connected open region. What is simply connected mean? Anybody know that one? Differential equations. Simply connected means it has no holes. Within the region can be drawn to a point without exiting the region. So if there's a hole in the middle, you can't draw it to every closed curve, that is. You can't draw every closed curve to a point. It'll put a curve surrounding the hole that will be drawn over the hole eventually. You can't even have a point missing. There are examples of open regions with a point missing in the middle, and this theorem doesn't apply. So on a simply connected, meaning no holes, then you can't draw a simple closed curve to a point. Region, open region. Containing I should put this second. Put this two ways. I'm going to put this one second. I think it fits better second. Not wrong yet, but on an open region, if f is conservative, then it turns out that dg dx equals df dy. That's the test. If it's conservative, it will always satisfy this equation. That's not really what we want to know. We want to know when is it conservative. So this is the second part. On a simply connected known holes open region. So you need this additional criterion that is simply connected, containing simply connected open region. If with these partial derivatives continuous, first partials. If dg dx equals df dy, then f is conservative. So that's what he was alluding to. Because you can test it beforehand. This was kind of hard to do two partial integrals and say, oh no, I can't make the mean, so it's not conservative. You can just test this instead. So in an example on our last case, f of x y is x squared y I plus 5xy squared j. This is your little f. This is your little g, just whatever multiplies I, whatever multiplies j, has dg dx equal 5y squared is not equal to partial of this with respect to y is x squared on an open region. You might, I don't like a curve x equals 1 over square root of 5y make it work, but it has this not equal on any open region, meaning C. Any curve. It's not this on any open region, so it's not conservative. That's the first part of the theorem. If it was conservative, these would be equal to. Then if I found these were equal on a simply connected open region, then I'd say, oh, it's conservative. Then I can find phi. So there's a quick test. Just see if the GDX is df dy. That's kind of hard to remember, but we'll make it a little more memorable as we get along. Let's try another one. I want to actually use our theorem now. So if it's any one of those three vector line integral forms, just write, dx dt dt or dr dt dt, those kind of things, and evaluate it along the curve using the parametric equations on the curve. But if it's conservative, you have this alternative. And here's another example. Same instructions for this one is this conservative. F of xy equals e to the x cosine y I plus or minus e to the x sine y j. Is that conservative? If so, find the potential and evaluate the line integral. Let's just say find a potential. No, that's it. And evaluate the integral from 0, 0 to 1, 1. Of this is the new notation. That's not any one of the three notations. How would I put that? It's because it's going to turn out to be, if it's conservative, you can just put the endpoints and use the endpoints to evaluate it. So this is another notation, a fourth if you like, that you can use what happens to be conservative, and it will turn out to be conservative. If it's conservative. All you need is the endpoints to evaluate it, so we can write it like that. It's the same as integral along C f dot VR. All right. So is it conservative? Well, this is F. This is G. We say dg dx is derivative with respect to x of minus e to the x sine y is minus e to the x sine y, right? Well, what's the f dy? That's also minus e to the x sine y. These are equal everywhere. Well, the whole plane is simply connected, is a simply connected open region. So R2 is notation for the real numbers Cartesian product with the real numbers plane. It's introducing some new notation here. So it's all ordered pairs of real numbers, what that means. Open, simply connected. So on the whole plane, since the g dx equals the f dy, this is conservative. Any curve whatsoever you can apply theorem to. Which means in particular, if I have a curve going from 0, 0 to 1, 1, maybe it's this one here. What's its value? I don't even care what curve it is, as long as it's piecewise smooth. Just need to find the potential. What is the potential? I have to integrate. So this is a good test to see before you integrate, but in the end, you have to integrate anyway if it turns out to be conservative. The fast test if you think it's not going to be conservative. But the theorem says that this is equal to phi at the final point, 1, 1, minus phi at the end point, 0, 0. And it doesn't matter which path I took. I could have taken this path, right? I can go twice around and over here. Any will have the same value of that integral according to the theorem. And we say it's path independent. It does not matter the path, twice smooth path, it just matters the endpoints. Where we have to calculate phi. Again, if this is f, oops, not this. This is f and this is g. We say phi is the integral of f with respect to x, right? Because this is supposed to be d phi dy, d phi dx. So we integrate with respect to x to get phi. This is supposed to be d phi dy. We integrate it with respect to y. And we know before we even start that we can make these the same because we already did the test. Well, this test proved that it's going to work. We just have to find out what the answer is. This time, so we could have avoided it. I just tried this, it would have worked. But we integrate with respect to x. Cosine y is a constant. It can come right out, right? Integral of e to the x is just e to the x. So this is e to the x cosine y plus an arbitrary constant, but in a partial integration, that's an arbitrary function of y. These are all functions of x and y whose partial with respect to x is this integram. respect to y, treating x as a constant. The minus e to the x comes out. And I integrate sine y and get minus cosine y. So I get e to the x cosine y plus an arbitrary function of x. So what is the potential? We have to satisfy both these equations. We need, and we know this will work because we tested the function by the theorem. And sure enough, these now match up. How can these two be equal then? Only if they're just constants. This one can't depend on y's, and this one can't depend on x. So between them, they just be a constant. E of xy is equal to e, so we'll put therefore, three dots being therefore, e to the x cosine y plus an actual constant c is all potentials. Just like in the fundamental theorem of calculus, where every antiderivative is equal to every other antiderivative function plus an arbitrary constant, just so potentials are all equal to within adding a constant. And after all, the fundamental theorem of calculus, we said, is a special case of this fundamental theorem of line integrals. All right, so this is all potentials. And therefore, the integral from 0, 0 to 1, 1, no matter what path we take, piecewise smooth. F. Just this function evaluated at 1, 1, e to the 1 cosine 1 plus c. We can leave off the plus c because we just want any potential. All give the same. Let's put it on plus c minus e to the 0 cosine 0 plus c, and the c's always cancel when you evaluate this. Okay. So it's easy. It's just to choose c to be 0, and you get e times cosine 1. There's the value of that line integral, no matter the path.
So when you circled the e to the x cosine y at the top, is it basically you're trying to find what they share in common?
Yeah.
And then determine it? Okay.
Yeah. That's an example actually out of the problems of the book. I want to do one more. It illustrates a little more.
If there were more than one term, like if there's an e to the x cosine y plus sine y or something like that.
That's
If
the
it
next
didn't have-
example.
Okay.
We'll do that in this example. That's why I said we need one more example. All right, so let's do, suppose I have this. Suppose the vector field 2xy plus 1 that's I plus x squared plus 2j. Is that conservative? We can test if it's conservative by doing the partial integrals, but maybe it's faster just apply the test, especially if we think it's not conservative. Right? So we'll calculate, we call this little f and this little g. We'll calculate dg dx and df dy and see if they're equal. The dg dx is evidently 2x, 2x plus 0. Oh, but that's df dy. They are equal. Now these are polynomials in two variables, so they're this holds on the whole plane. So we'll say on R2, the whole xy plane. So yes, it's conservative on the plane. So now part B, suppose I evaluate integral, this time going from 0, 0 to the point 4, 2. f dot dr with this f. Well, to do that, I need phi. Phi is the partial integral of this one with respect to x. So it's integral 2xy plus 1 with respect to x. Treating y as a constant, integral of 2xy is x squared y, right? 2xc has an integral x squared c, but c is y. And then an integral of 1 is just x. And then there's an arbitrary function of y. But also from the second part, d phi dy has to be this function. So phi is the integral of this function with respect to y, x squared plus 2 dy. The integral of x squared, treating x as a constant, is just x squared y. Integral of 2 is 2y. And then I've got an arbitrary function of x. How can I make these equal? These are the same, they match up, so phi is going to have that. But h of y must be 2y. K of x must be x. But then you can add an arbitrary constant in either of these. So phi must be x squared y plus x. Constant is all functions that match up all this stuff. So we knew from testing that dg dx equals df dy that it would work. When we actually calculate the partial integral, we find these are the functions that are potential. Put c equals 0 just for simplicity, because we only need one potential to evaluate the line integral. We can use whichever one we want. This one is less writing. This time we're going from 0, 0 to 4, 2, and it's path independent since it's a conservative field. So now, by the fundamental theorem of line integrals, beginning there, last time, the integral from 0, 0 to 4, 2 is also just it's just another notation for integral on c f dot dr. Just the book likes to use this notation equivalently when it happens in a conservative field. Of f dot dr, we can write it out. It's 2xy plus 1 x squared plus 2 dot dr, if you like, is just phi at final point 4, 2 minus phi at the initial point 0. That's all there is to it. Say 2 squared times 4 plus 4 plus 2 times 2. I plug in 4, 2 minus 0 when I plug in the other point. So it's 16 plus 4 is 20 plus 4 is 24. So there's a nice thing about the fundamental theorem of line integrals. For this special case, you can evaluate these easily. Provided you do the integral to find the potential. And here's a corollary that's really nice. If f is conservative on R, plane region R, with continuous components again. So that the integral exists. Is a piecewise smooth closed path within R. I should have said open plane region R just to be picky. And C is a piecewise smooth path within this open region that is closed. What does closed mean?
I'll do it all the way around.
Means it ends where it begins. So it goes in a big loop. It might cross itself, but it ends in it's a loop. Ends where it begins. So a simple closed curve is a curve that doesn't intersect itself. It's closed. I think we mentioned that before. So it ends where it begins. The integral along C, f dot dr, and here's yet another notation. If I put a circle here, what does it mean? It means the same thing, except it's a reminder to me that the path is closed. So circle means it's a closed path. Sometimes they'll put an arrow on here to indicate the direction, but it doesn't matter the direction for this theorem. What's the answer to this one? I think you know this one. What's the line integral of a conservative field around a closed piecewise smooth path? I said you get 0 or 1 all the time. It's 0 this time. All right. Losing your touch there. All right. It's 0. Why? The proof is by this. So this is a corollary. A good example. This would be corollary. What a corollary is, it's a theorem. You can call a theorem a corollary if it follows quickly from another theorem, right? So it's a corollary to the fundamental theorem of line integrals. It means we're going to prove it from the line integral theorem, right? It's because of this. It's real easy. In fact, I was going to do the proof of the fundamental theorem of line integrals. It's easy too. We can do that in a minute here. Proof of this one is that the integral around a closed path f dot dr is phi at the ending point, x0, y0, minus phi at the beginning point, x0, y0, right? It ends where it begins at the same point, x0, y0. You subtract those and you get 0. That's all the proof is. One step, one intermediate step. So that one's worth saying, right? And so, example, what is the integral around the simple closed curve xi plus yj dot dr, f dot dr like that. If the closed curve is the unit circle, counterclockwise. We'll start at this point 1, 0, and we'll go once around. You could do this by our beginning theorem, right? You could write the parametric equations for this as cosine t sine t to sweep out the unit circle and calculate f dot dr dt dt, right? And with much labor and sweat, come up, whoa, I did it. I can do it because it's an easy circle. But what could you do easier? You notice that the gdx equals 0 is the f dy. So it's conservative. By our corollary, this thing must be equal to 0. Since we integrated a conservative form around our closed path, that's integral is just 0. We don't have to do any work. So those are the nice corollaries for conservative fields with continuous components. Ending point, plugging the beginning point into the potential and take the difference. Integral on a closed path is 0, and the traversing there is path independent. Doesn't matter what the path is. You can take whatever one you want. It's still just the ending point minus the beginning point plugged into the potential. Now, what's an application of this, you might ask? Note, in the physical sciences, if F of xy is a force field, like a gravitational field or electromagnetic field or something like that, then W equals integral F dot dr along C is called the work done by F along C. We mentioned that last time. And we said that before, and phi of xy, or in physics, minus phi of xy is the potential energy. Gravity is conservative, for instance. That means your potential energy doesn't depend on what path you take, it just depends on what point you're at. If you go around in an orbit with a planet and get back to where you started, you have the same energy as when you began the orbit. Each time you come back to the same point, you have the same energy as before. That's the idea.
Is that the same symbol used for these two?
Flux around a closed, it's the same symbol, it just means closed path. The flux is a little different integral. Because it's a surface integral, but it's still over a closed surface, I guess, when you do flux. Flux to a closed surface, you use the symbol. So the circle still makes closed. All right. All right, well, and another alternative, here's a final alternative for the plane. Actually, one more thing to do here too, come to think of it. Maybe I'll do this first, and then I'll do the final alternative for the plane. No, let's go ahead and do this. So the next theorem is another alternative. I'll get back to three dimensions. Theorem, this is called Green's theorem. And Green is up on Wikipedia. It's a very fun story. He's also written up in your book. Here's the story of George Green. You can see that. Maybe I need to make it larger. People online. That's too big in there. It says George Green, 1793 to 1841, was a British mathematical physicist who wrote an essay on the on the application of mathematical analysis to the theories of electricity and magnetism. He sort of set up the way for James Clerk Maxwell to come along later and come up with Maxwell's equations that drive all our electronic devices we talked about before. So this theorem is named after him. Down below. Green's life story is remarkable in that he was almost entirely self-taught. He received only about 1 year of formal schooling as a child between the ages of 8 and 9. The rest of it he got by reading his dad's library and that kind of stuff. So he taught himself mathematics. Eventually, just move the camera. He eventually went to the university and got a degree. You can read that in your book. But he died not too long afterwards. But then afterwards, they found out he'd written this really great article that explained an important theorem that we now call Green's theorem. I'm trying to make the screen move down. I moved the camera down by mistake. There's his tombstone. Anyway, so you can read about him in here.
Someone found it after he died.
It was published. I can read it in here. It says in your book, I think, more about that. He became famous after he died, basically. But he initially published his article. It wasn't well read. It was a smaller local publication, and nobody knew about it until after he died, hardly. And Green published his essay. It sold on a subscription to 51 people, most of whom were friends and probably could not understand it. That's what it says here in the Wikipedia. But eventually went to university education connected to Cambridge. Became ill. Green's work was not well known. Green himself, the first mathematician to quote his 1928 work with this theorem, was Robert Murphy. 1845, 4 years after Green's death, Green's work was rediscovered by young William Thomson, then age 21, known as Lord Kelvin, who popularized it for future mathematicians. Anyway, so it sort of slipped by for a while. Well, let's see what his theorem says here. Oops. All right. Hold on. So now here's Green's theorem. Let's start right here. F of x, y has continuous parcels on open R containing that is simply connected. Again, no holes. And bounded by a piecewise smooth simple closed curve C in R then you can evaluate the line integral like this. Which is important, right? Because it's work, for instance. When you asked about flex, actually, if you're doing flex 2 dimensions through a plane curve, and that notation does apply here. I have to get to that. We're on a closed curve. C. Oh, and then taking counterclockwise, I need to put on. There's a lot of things on here, but they mostly amount to continuous and closed. Taken counterclockwise, though, is the other thing. Then the work around that path, or the line integral around that path, is the double integral over R, dg dx minus df dy. This proof is longer. I'll admit it. I'm going to prove the fundamental theorem of line integrals. All right, that'll be Green's theorem. That needs a picture because all that writing is like 1,000 words, right? So we must need a picture. So, but the idea is this: you have a simple curve is one that's not self-intersecting. We didn't say that, did we? We sort of spoke of not self-intersecting, so it doesn't make a figure 8 or something. Closed means it ends where it begins. Simple means it's not self-intersecting, except it's closed, it ends where it begins. So it's a curve like this. And without intersecting, it can have a finite number of corners in it. But it's piecewise smooth, and there's no finite number of corners like that. So this is the curve C, and it's the boundary. I put in R, I should say bounding R here. So this bounds R, then you can evaluate the line integral around this closed path. So Green's theorem only applies to closed paths, and it only applies to counterclockwise. However, clockwise, remember, just minus the integral counterclockwise. So you can apply it to clockwise by putting a minus on here. You can evaluate the single integral by doing a double integral instead. How about that? How can that be better? Now you got to do two integrals, right? But actually, on some regions, like if this region is a rectangle, it might be easier to do the integral over a rectangle with constant endpoints, a double integral, than to do four pieces along the edges with this one. So it is actually very nice in these things where you have to evaluate integrals around a closed path. And so let's try an example. Now you have these alternatives. You can go to the basic thing where you replace the R with the RDT and integrate from A to B. If the thing is conservative, you can apply fundamental diagonal line integrals. Otherwise, you can apply Green's theorem. And Green's theorem actually, but since it only applies to closed paths, it just in the conservative force, these two are equal, and you get integral of 0 is 0. So Green's theorem only says that the line integral is 0 for a conservative force. And this is really used then for non-conservative forces. Suppose I have this problem. Suppose I want to evaluate the non-conservative, the integral work done by the non-conservative force. Y squared dx plus x squared dy. Non-conservative field along the closed path C, where C is this.
Can you move the camera, please?
Oh yeah, thank you. Where C is this curve here taken counterclockwise around the semicircle of radius 5. Up here and along the x-axis here. This one is nice for Green's theorem because if you wanted to do it by the definition, integral f dot dr, what would you have to put? You have to put dx dt dt and dy dt. 5 cosine t and 5 sine t for the semicircle, and then parameterize this one separately, like x equals t and y equals 0 along this path. And you can do it. Maybe we'll do that if we get enough time here. But Green's theorem makes it a lot easier. By Green's theorem, if we want to integrate the thing along the integral along C, we can instead integrate this integral over the enclosed region R. That it enclosed, that's C is the boundary of. And we can say this is equal to the line integral. Well, this is G and this is F. So it's dg dx minus df dy. 2x minus 2y. Right? G dx df dy. Double integral dA over the enclosed plane region R. All right. Well, since this is a semicircle, we might want to do this in polar coordinates, and we'll say this is then equal to the double integral, we'll replace x with r, y with r sine theta. And then I need integrate r dr d theta. And what do I do to make this a simple polar region here? I can go from this angle, this ray, theta equals 0, turn around to this ray, theta equals pi. Between an inside radius, r equals 0, and an outside radius, think of this thing coming out here, you go from the inside curve to the outside curve, r equals 5. I'm going to integrate r from 0 to 5, inside curve to outside curve, and theta from 0 to pi, beginning angle to ending angle, thinking as a simple polar region. And now I can do it. We can rewrite this. Now let's just do it as it is. This is integral from 0 to pi. 2 comes out. Integral 0 to 5 of r squared times cosine theta minus sine theta dr d theta. I'm right, pulling this all together. I guess I better erase my region. And now you realize, wait a minute. This is constant inside integral, I can pull it out. Since it's evaluated constant endpoints as a constant, I can pull it out. And we can rewrite this as twice the integral from 0 to pi d theta times the integral from 0 to 5. Oops, not d theta. Cosine theta minus sine theta d theta. Times the integral from 0 to 5, r squared dr. All right, so integral of cosine is sine. Integral minus sine is cosine. And then that's multiplied by r cubed over 3, evaluated as 0 to 5. Now, if you think about it, on 0 to pi, cosine looks like this. And the area above the x-axis is equal to the area below. So the line integral is this area minus this integral area is 0. So I drop this one out, it's going to integrate to 0. This one. Let's run this up here. I could have dropped cosine out from the beginning because its integral from 0 to pi is going to be 0. I shouldn't bother to do that. Anyway, this one's going to fall out. But I then need to evaluate cosine at pi and 0. Or you could say sine is 0 at both these endpoints. So it's twice. Cosine at pi is 1. Cosine at 0 is, cosine at pi is minus 1. Cosine at 0 is 1. That. 2 times minus 2 times r cubed over 3 is then phi cubed over 3. Yeah, 125 times 4. I think it's been 500 thirds. That's. See if I've got this right, Don. Yeah. Yeah, so minus 500 thirds. The Green's theorem then allows you to evaluate the single integral by doing a double integral over the region that encloses. Now we should mention one more thing, that these extend to 3 dimensions, not Green's theorem. There's an analogy to Green's theorem in 3 dimensions, which is
Is that picture given to you, or did you make it based off of the like F and G? Like you already erased it, but the semicircle?
yeah, the semicircle is supposed to be given. You have to have that. integral around a curve, and we're saying that the curve is the semicircle top and the line segment bottom, that's given.
Okay.
So you say find this integral with this f and that curve given. So now note this extends to 3 dimensions. I'm gonna have to do the proof of the fundamental theorem of line integrals next time. Not long, but anyway. Note in 3 dimensions, there's a similar theorem. Green's theorem is extended as analogy by Stokes' theorem, to be discussed. And the fundamental theorem of line integrals just extends naturally. For f, a function with 3 components of 3 variables, x, y, z, equals the gradient of a function phi of 3 variables. So it's conservative. Well, again, it's simply connected reason domain in 3 space. The line integral f dot dr in 3 dimensions along the curve is equal to phi at the final endpoint, x1, y1, z1, minus phi at the initial point, x0, y0, z0, for c from the one point to the other. So it has the same analogy, just with one more dimension. But a different test. On a, and then it works like this. If f a function of 3 variables in 3 space is conservative, then you extend what we had before, and it turns out that the curl f equals 0. Remember what the components of curl are?
Gradient.
Yeah, it's a gradient operator across f. So if f has 3 components, it's f of x, y, z, I plus g of x, y, z.
Can you move the camera, please?
Yeah. Plus h of x, y, z, k. For that f, what you want is let's see, d dy h minus d dz g I minus, or well, let's say plus, minus d dy dz f j plus the g dj. Let's see, this was z. This was, yeah, I wrote this backwards. This is f dz minus, trying to do this too fast, minus dh dx, looks like that. And this is dg dx minus df dy. Okay. So you need this equal to 0, which means that all three of these components equal 0. And now you realize something. If you have something f in a plane, then these two are 0, and you just get the first theorem we had that for a force field in a plane, you need dg dx minus df dy equals 0 in our previous theorem. It extends this way to 3 dimensions. It'll be conservative. If it's conservative, then the curl will be 0. All three of these differences will be 0. And on a simply connected open region, and simply connected now, it doesn't mean it can have holes. It can't have a hole clear. So you can have a sphere within a hole within a sphere. You can still drive every loop to a point by drawing it around the inside sphere. That's still simply connected. But you can't have a sphere with a hole clear through it, because then you can't draw a loop to a point. So simply connected still has the definition. Every loop within the region has to be drawable to a point. And on a simply connected open solid W, if curl of f is 0, with f having continuous components, f, g, h, then f is conservative. All right. So that's the generalization to 3 dimensions. It's the same stuff. It's just that instead of dg dx equals df dy, you have this generalization that the curl of x has to be equal. Imply on a simply connected solid that it's conservative. Well, I guess that's a good stopping point then for tonight. I failed to bring the problems, however. Let me send the problems by email, then I'll send those out shortly here. I don't have the problem set with me. It's all chapter 15 now. It's our last chapter.
Section of the chapter.
Yeah, I'm just trying to remember. Yeah, I think 15.2 was line integrals. 15.3 was conservative line integrals, and 15.4 is 15.3, 15.4 both. Okay, thank you everybody online for coming out, and I'll send out the homework by email.